Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 4-5 Extra Practice Number 4 solutions on logarithmic equations. This one has a puzzle that goes with it. Let's go ahead and check that out. For this puzzle, we're trying to solve the riddle of what did the vampire doctor say to his patient. So we have to solve these different logarithmic equations below. And whenever we get an answer, we look up the answer down here and put the letter next to the problem above that answer. So if I do problem n, for example, and I think there's only one of each letter. If we do problem n and end up with an answer of, I don't know, 4, then we would put n above the 4 here. So let's go ahead and see what's going on with this vampire healthcare. So here we go with our first problem, which is problem n. Now my strategy on all of these is going to be pretty much the same. I'm going to try to get a single log, at most one log, on each side of the equation, and then I'm going to raise both sides of the equation. I'm going to raise actually the base of the log to both sides of the equation. So in this case, my log is already isolated. I've got a base of 3, so I'm going to do 3 to the left side of the equation equals 3 to the right side of the equation. So 3 to log base 3 of 2x minus 1, and 3 to this 3. This 3 became the exponent on this base 3, just so we don't get those mixed up. So when I raise a base to a log with the same base, those cancel out. That's why I'm doing this. And then I'm ending up with 2x minus 1 on the left side. Right side, I've got 3 to the third, which is 27. And now if I add 1 to the other side and then divide by 2, I end up with 14 for my final answer. Now, one thing I'm going to do at the end of all these, mentally at least, is I'm going to plug my answer back into the original just to make sure that I'm not taking the log of a negative number or a 0. Because if I am, I'm going to have to throw that answer out. And you'll notice down here below, there are some that say no solution. And each of these has at most one answer. So I might end up having to throw out some solutions along the way. Now I did get a solution of 14. Plugging that back in here, that's not going to give me 0 or a negative inside a logarithm, so it's a good answer. That means that I'm going to be putting an n next to 14, and I see one of those right here. One other thing we need to be careful about is there are multiple of some of these numbers down below, so we may end up using an answer more than once. For problem O, we have a log on each side of the equation. Because it's the same base and because there's only one log and that's it on each side, I can actually raise 7 to both sides of this equation right off the bat. So if I do that, that cancels out my log on the left, giving me 3x minus 1, and it cancels my log on the right, giving me x minus 3. Now I'm just going to get the x's on one side and the numbers on the other. 3x minus x gives me a 2x on the left side. And then if I add 11 to the other side, negative 3 plus 11 is 8. So then x equals 8 over 2, or 4. Plugging 4 back in here, we've got 12 minus 11, that's okay. 4 minus 3, that's also non-zero, non-negative. So I put an O above 4 then. We've got one of those right here, and actually another one over here. For problem number H, or letter H, I notice now that I have 2 logarithms on the same side. So what I'm going to do to fix this situation, because I really only want one before I start raising bases to sides here, I want to combine this into one logarithm using my log rules. Since I'm adding these 2 logarithms, I can multiply the things inside. So I can call this all log base 6 of 3x equals 2. Now I'm going to go ahead and raise my base of 6 to both sides. If I do that, on the left side, the log and the 6 cancel, leaving me with just 3x. On the right side, 6 to the second power is 36. And then dividing both sides by 3 to get x by itself, we end up with 12. If I plug 12 back in here, I'm only taking logs of positive numbers, so that's a good answer. Let me then put an h above 12 right there. For this next problem, we actually have a few different things we could do here. Since I have a log and only one log on this one side here, I could, if I wanted to, raise 2 to both sides right away. But if I do that, then I'm going to have to expand this x minus 3 cubed, which is going to be a huge nightmare. I could do it, but that's going to be a mess solving that. So what I'm going to do instead in the beginning, I'm going to use another rule of logarithms, the pop-out rule, which means if there's something inside here raised to a power, I can pop that power out as a multiplier in front of the log. So I'm going to turn this left side into 3 log base 2 of x minus 3. And then if I do that, I still need to get this log base 2 by itself because it's no longer by itself. It's got this 3 right here. I'm going to divide both sides by 3. 6 divided by 3 is 2, so that actually wasn't that hard. At this point, I'm going to raise 2 to both sides of the equation. This is going to give me a much nicer equation to solve. So if I do that, my 2 and log 2 are canceling on the left side, leaving me with x minus 3. On the right side, 2 squared is going to be just 4. And then adding 3 to the other side gives me 7. Checking that by plugging it back in, 7 minus 3 is a positive, so that's good to go. Let me just put s now in the spot 7 right here, and there's only one of those, so on we go to the next one. This next one, problem F, is another one where you can definitely save yourself some trouble with a little bit of log rule trickery in the beginning. I'm going to start first off by dividing both sides by 4. I'm doing that, I guess there's a few different ways I could do this. I'm just kind of thinking ahead. If I divide both sides by 4, that's going to give me a 1/2 out here, which I can then put inside on the 9, which is going to be nice, give me a smaller number. Alternatively, I could divide both sides by 2, but then that's going to give me a 2 over here, which I'm then going to have to put on the x, and I'm going to have an x squared equaling something, which is a little bit messier to solve. So, divide both sides by 4. That gives me log base 8 of x on the left, and 1 over 2 log base 8 of 9 on the right. And then, just as I said, I'm going to move this 1/2 in as an exponent on the 9 using my pop-in rule. Now, the 1/2 power is actually the square root. So I've got the square root of 9 going on in there, which is pretty easy to figure out. At this point, I'm going to raise the base of 8 to both sides, and while I'm at it, I'll simplify this radical 9 to be a 3. So I've got a 3 there instead of root 9 now. Both of these 8s cancel out the log base 8s, so I end up with x on one side and 3 on the other. So just x equals 3 then would be my answer. If I plug that in, log of x, or log of 3, is just fine. I can do that. That's not going to be undefined. So I'll put an f then above spot 3. So we've got one right there and another one right next to it. For this next problem, I've got logs all over the place. Before I raise the base, which actually is an invisible 10 because they didn't write any number, before I raise 10 to both sides of this, I'm going to need to get at most one logarithm on each side. So the left side needs to be combined into a single log. Since I'm adding these logs together, I can multiply the things inside. So that's going to give me log of, and if I distribute this x, that's going to be x squared plus 2x inside that logarithm equals log 3. Now that I have a single log on each side, I'll raise 10 to both sides. That cancels out the logs on each side, leaving me with x squared plus 2x equals 3. This is a quadratic equation. It looks like it might be factorable, so let me move everything over to the left side. And now I'm looking for factors of -3 that add up to 2. So if I have 1 and 3, -1 and +3 would do it. So this is going to be x minus 1 and x plus 3 equals 0. Setting each of these equal to 0 and zeroing them out, I end up with x equals 1 and -3. Now again, you might notice that there's no answer choices that have both of those. So one of these is probably bad news. Let's double check by plugging these back in the original. If I plug 1 in, log of 1 and log of 1 plus 2 is fine. That doesn't cause any issues. Now if I plug in -3, log of x really means log of -3 in this case, which would be undefined. Since -3 makes the original undefined, it's an extraneous root. I have to cross it off. And then 1 is my only true answer. So there's a 1 right here down below. I'm going to put an I in that spot. Here we go now with problem A. This is one where you could follow kind of the strict log rules and make a huge mess for yourself in the beginning. For example, you could pop this 2 in as an exponent and have x plus 6 quantity squared. Then you could merge this all into one big log by dividing x plus 6 squared by 16 inside the logarithm, and then you're going to have a little bit of a quadratic to deal with when you raise 2 to both sides. So that's one option for solving this. I chose to do something different. I noticed that I had log base 2 of 16. So I actually can simplify that a little bit. This is just asking 2 to the what power equals 16, and that's 4. So I'll just turn this into a 4 right here. And then I also noticed that I can just add this 4 to the other side, because like why not? So that'll give me a 6 over there. And finally, I noticed that I can deal with this 2 by dividing both sides by 2. So that'll give me log base 2 of x plus 6 equals 3. This is a much nicer thing to work with now. Let me go ahead and raise the base 2 to both sides of this. So we have 2 to this log expression and 2 to the third. The 2 in the log cancel, that's just x plus 6. And then 2 to the third is just 8. And now solving this just means subtracting 6 from both sides, so we end up with x equals 2. Plugging that back in just to be careful and check, 2 plus 6, the log of that's going to be fine. So let me go ahead and now put an a in spot 2 down here. For this next one, we have 2 logarithms on the same side of the equation. There can only be one. So what are we going to do? Unlike the last problem, I can't just get rid of one of these logs by simplifying it. This time I'm going to have to combine them using my log rules. When we subtract logarithms, we're allowed to divide the things inside them. So I can rewrite this as log base 4 of x squared minus 4 over x plus 2. That's all inside one big logarithm on the left. Now before I go ahead and raise 4 to both sides, if I do that, I'm going to have to multiply by x plus 2 and then solve a quadratic. One thing I'd like to do instead, x squared minus 4, that looks factorable. That's a difference of squares. I can actually factor that using my plus minus shortcut. So this will be x plus 2 and x minus 2. I'm going to do all that inside the logarithm before I do anything else. I'm allowed to do that. And now I notice that these x plus 2's can actually cancel out. So this is just log base 4 of x minus 2 equals 2. Now if I raise 4 to both sides, that's going to give me something nice to solve. So if I do that, the log cancels out on the left side, leaving me with x minus 2. On the right side, 4 squared is going to give me 16. And then I just have to add 2 over there, and I get x equals 18. 18 squared minus 4 and 18 plus 2 are both positive numbers that I'll be taking the log of, so that's just fine. That means that c can go in spot 18 here. This next one is kind of fun. We've got 2 logs on the same side. Again, we can't let that stand if we're going to raise 2 to both sides, so we have to combine these into one big log, and I can't get rid of them through other means. Since I'm subtracting, that means I can divide 5x plus 7 by x inside one big logarithm here. And unlike the last problem, there isn't really any way I can simplify this expression by factoring and canceling anything out. I could split it up into 5 plus 7 over x if I divide each of these by x, but I'm not sure that's something I want to mess around with after things are settled after getting rid of the log. So I'm just going to go straight to raising 2 to both sides of this equation. Doing that gives me 5x plus 7 over x on the left side, and on the right side, 2 to this 2 here is going to be 4. Next thing I'm going to do is multiply both sides by x to get rid of this fraction, so that's a 4x over on the right side. And now I'm just going to get the x's on one side and the numbers on the other. I'm going to move my x's over to the left and my constants over to the right. So 5x minus 4x gives me an x on the left side, and if I subtract 7 to get it over to the right side, that gives me negative 7. And then I've actually discovered that I've already solved this equation. It's just x equals negative 7. Cool. Now, if I plug that back in, log base 2 of negative 7, I'm going to be taking the log of a negative right there, and probably also in this other one as well if I plug negative 7 in. So this is making the original undefined and I have to cross off that answer. Unlike the last problem where we had an extraneous root, in this problem we don't have any other answers left over. Since there's no answers, that means this is no solution, which means t is going in these no solution spots. There's 3 of them, so one right here, here, and here. That one took a little work, but it paid off in the end. For the final problem here, I think we know first off where letter P is going to have to go because there's only one blank left. But let's play it out here and get the actual math right. For this one, we have not 1, not 2, not 3, but 4 different logarithmic expressions. So we want to narrow that down to only 1 on each side at most. So I'm going to do that since I'm subtracting both of these logs here by division. The left side, I'm going to have log of x plus 5 over x minus 1. On the right side, I'm going to simplify this to log of x plus 2 over x minus 3. And there isn't really any other simplifying I can do. I'm just going to raise 10, the invisible base 10, to both sides here. So on the left side, I've got x plus 5 over x minus 1, and on the right side, x plus 2 over x minus 3. All right, where to go from here? Well, we have 2 fractions with an equals between them. So kind of going back in time, one of our old algebra tricks is cross-multiplying in this situation. So I'm going to do that. So on the left side, I'll have x plus 5 times x minus 3. And on the right side, if I move the x minus 1 over here, I've got x plus 2 times x minus 1, in whatever order I want to write it. At this point, there's nothing else to do except for FOIL each of these out and move things around afterwards. So on the left side, we've got firsts gives me x squared. Then we have a negative 3x. Inners gives me a 5x, and the lasts is going to be negative 15. On the right side, we have an x squared, 2x, negative 1x, and then negative 1 times 2 for negative 2. Well, this is a lot. Let's simplify each side by combining like terms. So on the left side, we have x squared plus 2x minus 15. On the right side, this is going to be x squared plus x minus 2. And now let me go ahead and let's see here. This is a quadratic. So normally I would move everything over to one side and then use factoring or quadratic formula. But one thing I happen to notice is if I start moving things over to one side, we have an x squared and an x squared. When I subtract one of these x squares, those are going to go away. So although this started as a quadratic, it actually is really only a linear equation in disguise. So those x squareds are going to cancel out, which means I'm just going to move my x's over to one side and my constants over to the other side. This is just a linear equation. So we have 2x minus this x giving me a 1x on the left side. And then if I add the 15 over here, negative 2 plus 15 gives me 13. Just double checking for the sake of argument, if I plug 13 into all these different logs, we have 13 plus 5, 13 minus 1, 13 plus 2, and 13 minus 3. All of those are going to be positive things that I'm taking the log of. So 13 works, and I can put a p in that last spot and feel good about it. There we go. And now at long last, we've filled in all the blanks. We can solve the riddle. What did the vampire doctor say to his patient? We have stop that coffin. Stop that coffin. Blah, blah. I do not say blah, blah, blah. All right. Till next time, Mr. Sutton signing it off.